Hey everyone, it's a real pleasure to be here at this year's Airflow Summit. One more time, huge thanks to the organizers for making it happen. Even though we couldn't join in person in Seattle, the MLOps team is here today to share how we built an MLOps platform on more than 300 machine learning and data science specialists based on Airflow. So let's dive right in. But first, let's get to know each other a little bit. My name is Alexander Shirokov. I graduated from Itmor University and MCU University, and I work at Wildberries, one of the largest online marketplaces. I lead the MLOps team in the Work6 department, and which drives over a third part of the company's total revenue. For the past 3 years, our mission has been simple and ambitious: to launch AI products and build machine learning infrastructure and tools for over 300 machine learning and engineers across the company. What makes our team special is how closely we work with real products. Side by side with product managers and developers on the things like search by photo, so the infrastructure we build directly impacts business metrics and drives real value. That's why we always design our systems with usability and speed in mind. And MLOps Airflow is no exception. But of course, I'm not here alone today. Joining me are my teammates.
Thank you, Alexander. Hello, everyone. My name is Alexey Tarasov, and I'm a senior MLOps engineer in the inference stream team. In this project, my role has been threefold. I'm an engineer behind our Multicluster Airflow platform. I author the CI/CD pipelines that our data scientists use daily, and I'm responsible for taking real-time ML services to production. Thank you.
Hello everyone, my name is Roman Homenko. I'm senior MLOps engineer at Wildberries. My primary focus is the development of our internal MLTool library.
So, today we are going to cover three main things. First, we'll start with a bit of background, why we even built MLOps Airflow in the first place and how it's grown into what it is now. Then, we'll talk about how we managed to scale it up thanks to a well-designed multi-cluster architecture and CI/CD approach. And finally, we will show how we extended our Airflow with features that make it faster, safer, and simply more pleasant for data scientists to use. So, all right, let's start with the first part, why we needed it and what we've built. What is the problem we're actually trying to solve? At Wildberries, we have, as I said before, over 300 machine learning engineers, each working with their own tech stack, their own models, and often training or fine-tuning models directly in production, each within their own domain. But there was no single convenient orchestration solution. Some teams relied on cron jobs or ad hoc scripts, and which, as you can imagine, quickly became a nightmare to maintain. At the same time, we also needed to account for data engineering and analytics pipelines, so whatever we built had to work for them too. And we had to do all of this within our existing infrastructure, across multiple GPU-enabled Kubernetes clusters, with namespace-based access control for teams, with secure CI/CD, proper secrets management, and only, it's important, using stable open source tools that we could easily customize to fit our needs. A lot of them came together as MLOps Airflow, a unified orchestration platform that is scalable, resilient, and easy to use for data scientists. And as you'll see on the next slide, it's already been used a lot. Originally, we built this platform just for our own department, but it turned out to be such a good fit that it quickly spread across the company. Now, over 20 teams from different departments are using it, and there are already more than 400 DAGs running in production. And that's especially cool is that these DAGs aren't just owned by machine learning or data science teams. A lot of them come from data engineer and analytics as well. Because with our version of Airflow, you can pretty much do everything. Anything you want, exactly anything related to offline processing. You can pre-compute offline recommendations. It's a typical task for us, for our department, or fine-tune machine learning models. Run ETL pipelines for data engineering or aggregate large features with SparkSubmit. You can prepare analytical dashboards, run labeling pipelines for large language models, or even compute embeddings offline for text or computer vision model for upcoming A/B testing. Basically, anything you want to run offline, you can run it out on MLOps Airflow. And the best part of it, you can do it entirely on your own as our user. And we managed to make it possible thanks to a few core principles and technologies. Let's take a look at them. So, firstly, we made sure we can confidently roll out updates to the platform and scale it across multiple clusters, especially new clusters, whenever needed. Easy to deploy and scale for us. Secondly, for our users, it had to be simple, transparent, and fully self-service. They should be able to run, debug, and manage their own workflows without depending on us, MLOps team. And of course, we wrote tons of documentation to make that possible. And third, both for data scientists and for our own MLOps team, the development and testing process had to be easy, reproducible, and version controlled. So, how did we actually achieve that all? Let's finally dive into the technical architecture behind it. Alexei, it's your turn.
So what exactly are we building? We have created a comprehensive MLOps platform centered around a multi-cluster Airflow architecture with robust CI/CD processes. This isn't just about running Airflow. It's about building a reliable foundation for machine learning at scale. But why did we need this complex setup in the first place? The challenge was straightforward but critical. With separate Airflow instances in each Kubernetes cluster, we faced absolute chaos, messy deployments, disorganized dark syncing, and no single entry point for our users. Our goal became clear. We needed to build a unified orchestration platform that was scalable, resilient, as it was mentioned before, and most importantly, easy for our data scientists to use. So how did we solve this? Here is our architectural approach. We built a multi-cluster architecture with a single Airflow web UI that serves as the one entry point for all our users. Behind it, we have a centralized Postgres and Redis instances for metadata and task queues. The key innovation was separating our deployments. We have one of the core Airflow components and another that deploys only workers to our various Kubernetes clusters. All of this is powered by Celery Executor, which lets workers in different clusters pull tasks from central queues. Now you might be wondering, why Celery Executor specifically? Let me dive deeper into that decision. We choose Celery Executor over Kubernetes Executor for one main reason, flexibility. While Kubernetes Executor is great for isolation, it ties you to a single cluster. With Celery Executor, we can have multiple queues in Redis, each consumed by workers in specific Kubernetes cluster. This gives us horizontal scalability within each cluster while maintaining the ability to distribute workloads across different environments. But having workers across clusters is only part of the story. We also needed perfect isolation for each individual task. That's where our extended Kubernetes pod operator comes in. It gives us complete dependency isolation since each task runs in its own pod with its specific Docker image. We get incredible flexibility in resource allocation and can add special functionality to any task. Here is a real example from our production environment. We have a task that requires specific NVIDIA GPUs. With our operator, we can specify exactly which nodes to use, ensuring the task runs on the right hardware while still benefiting from our multi-cluster architecture. Now that you have seen the runtime architecture, let me show you the development experience we have built around it. This brings us to the development infrastructure and CI/CD, the backbone that makes everything work smoothly for our large team of specialists. Let's start with how we handle dev development and deployment. Here is our CI/CD magic. While Airflow syncs with a single GitLab repository, our data scientists develop DAGs across dozens of different projects. The bridge is our custom deploy script. When a data scientist merges their code and creates a GitLab tag, the script automatically copies their tag to our main Airflow repository. Each project maintains its own Docker image and dependencies, giving us flexibility while ensuring everything eventually flows into one centralized location. This streamlined workflow seems nice, but it runs on a critical foundation, a secure internal software supply chain. Let me show you how we build it. We use self-hosted private Harbor and Nexus repositories for Docker images and Python packages. This does two crucial things. It protects us from supply chain attacks, since our CI runners have no internet access, and it makes everything incredibly fast through local caching. We also provide standardized base images, both CPU and GPU versions, with key libraries pre-installed. This ensures everyone starts from the same foundation with consistent versions across the board. With the foundation in place, how do you help new team members get started quickly? We created what we call our DAG in 5 minutes template using Copier. It's incredibly simple. You run one command, answer a few questions, and instantly get a production-ready repository. This includes a working DAG example, ready-to-use Docker file, make file with common commands, and pre-configured CI/CD. The result, a new team member can deploy their first DAG in under 5 minutes. Of course, speed is nothing without quality and safety checks. And that's why we have robust quality gates. We run linters, unit tests, and Docker build tests. But the most crucial check is our custom DAG syntax validator. This clever script pulls actual variables and the connections from production and tests DAG imports in a realistic environment. It catches syntax errors, import issues, and configuration problems long before anything reaches production. This safety net means our data scientists get immediate feedback and we maintain platform stability. Now, let me show you the final piece of our deployment puzzle. When DAGs are deployed, we preserve the original commit history using GitLab CI variables. This means we maintain full auditability. We always know who changed, what, and when. We also inject valuable metadata directly into DAG files. As you can see here, each DAG carries information about its source repository, commit author, and version. This makes troubleshooting much easier and versioning completely transparent. So you have seen the engine of our platform. Now let's look at its steering wheel and dashboard. I'm handing over to Roman, who will tell you about our data science library, MLTool, the very layer that allows data scientists to work comfortably with everything I just described, including our custom Kubernetes operator. Thank you.
Now let me introduce our MLTool library. It's designed to simplify the life of our data scientists within our platform infrastructure. The core of this library is a flexible operator factory that allows data scientists to run the tasks seamlessly in a Kubernetes cluster. Here are its key features. First, it enables rapid deployment of DAG to Airflow. Second, it automatically selects the appropriate production or test Kubernetes cluster based on the current environment. It handles automatic data synchronization between tasks via S3, and it provides straightforward integration with Vault, allowing secrets to be injected directly into the pod. But that is not all. To address running Spark jobs, we built a dedicated factory on top of our pod operator factory. its key advantages are the ability to run Spark jobs on any of our Hadoop clusters, built-in Kerberos-authentication, automatic creation of Python environments, and secure delivery of secrets from Vault to Spark jobs running on the cluster. We'll take a closer look at the SparkSubmitOperator factory implementation a bit later in the presentation. Now let's take a look at our Vault integration. From the data scientist perspective, it's incredibly simple. All we need to do is provide a dictionary containing the path to the secrets and names to process. The process of retrieving these secrets works in three clear steps. First, based on provided Vault vars dictionary, we dynamically generate a configuration file for the Vault agent. Next, this Vault engine runs as a init container before the main container starts. Its job is to fetch the secret and write them into a shared volume. Finally, when the main container launches, it simply sources the secret from its shared volume. The entire process is completely transparent to the data scientist. We just provide the dictionary and the code gets secure access to the secrets. Another example of our custom logic is enable seamless data transfer between tasks within a DAG. For this, we've chosen S3 as the backbone. The requirements for the data scientist are straightforward. Specify the S3 path for upload and download data, ensure the Docker image has S5 CMD utility installed for efficient S3 operations. What happens under the hood? The framework automatically injects the necessary S3 upload or download commands before and after the data scientist's main task command. This creates a fully automatic pipeline stage without any extra code from the user. Another common request from both our data scientists and data engineers was the ability to run Spark tasks on our Hadoop clusters. The requirements for our implementation are as follows. Firstly, full compatibility with existing pod operator factory, an interface identical to the standard Airflow SparkSubmitOperator. Support for running Spark tasks on multiple distinct Hadoop clusters with minimal code changes, unified Spark base images across the platform, automatic creation of Conda environment based on PyProject TOML configuration file, secret injection into the Hadoop cluster when using deploy mod cluster on Spark Submit. To support multiple Hadoop clusters, we built a set of dedicated Docker images, each containing the required version of Hadoop Spark and the specific configuration files. The core of this solution is the SparkSubmitOperator factory. Its power lies in its extensibility through specialized pod builder subclasses. Each of these pod builders is responsible for generating a specific set of parameters, such as init containers, volumes, or volume mounts, which are then passed to the core pod operator factory to construct the final Spark task pod. This design gives us a flexible plug-and-play system. For example, we can easily add a init container to obtain a Kerberos ticket for authentication, or a git sync init container to pull the latest code directly from GitLab repository. Now, let's walk through the job submission flow. First, specified pod builders generate all the necessary low-level parameters for the pod operator factory. This is how we seamlessly integrate features like Kerberos token retrieval, similar to our Vault integration. Additionally, if project doesn't use Docker images, we can trigger code synchronization from GitLab before the job starts. And to simplify debugging, we can automatically generate a conda environment on the fly from the project PyProject toml file. Finally, the factory takes all the user-defined parameters and constructs a complete Spark submit command. This command is executed in isolated pod launched by our reliable pod operator factory. Now let's talk about security and access control. We've implemented straightforward ABAC system. Here's how it works. First, at the DAC level, we enforced rule every DAC must have team tags defined in its code. This is automatically verified during deployment. These tags are crucial because they directly determine the DAC's usability for specific teams within the Airflow database. For the user, the process is simple. They just need to be assigned to corresponding groups in Keycloak. On the Airflow side, our custom Keycloak security manager handles user authorization and fetch the group membership from Keycloak. Finally, the actual filtering happens at the database level. Based on the user group, a special mechanism filters a list of the DACs, ensuring the web interface only display what the user is authorized to see. And now Alexander will summarize our findings.
Yeah, thank you, Roman. So let's wrap up our story about MLOps Airflow. Thanks to Airflow and a stack that we built around it, we managed to build a scalable, reliable, and generally enjoyable platform, one that people actually want to use. But this didn't happen by accident. We put a huge amount of thought and care into the architecture and user experience so that our users can focus on their work and we can be proud of what we built. And we are not stopping here. In our backlog, we already have plenty of ideas to make the platform even more powerful. For example, a free resource-based scheduler that automatically selects a Kubernetes cluster with available capacity for a given pipeline, and an Airflow calendar to help users see when their DACs can safely run without conflicts on Kubernetes cluster. That's all from us.